The deletion, why reality is running out of space. The alert came at 2:14 a.m., a whisper from beyond the line we're not supposed to cross. The instrument logged thermal noise. The grad checked again. Same spike, same time, then nothing. Her note read, signal fades at the edge, cached elsewhere. What edge? The one that acts like a quota, where the universe keeps its ledgers. Meanwhile, a different team stared at impossible galaxies that shouldn't fit the budget this early. And in an older archive, NASA's anomalies sat redacted, then quietly footnoted. If reality is deleting to stay under limit, what gets erased? Where does it go, and can we prove the quota? The ledger on the edge, horizons as storage quotas. To understand deletion, we go straight to the boundary that counts, a horizon, not a brick wall and a counting line. Black holes taught us the trick decades ago. Entropy scales with area, not volume. For a hole, it's the event horizon's area measured in Planck tiles. Fewer tiles, fewer possible microstates. That was weird enough. Then De Sitter space, our accelerating cosmos, whispered the same rule. A cosmological horizon for any static observer, a faint Gibbons, Hawking temperature, and an entropy again tied to area. Different horizons, same ledger logic. Stakes up front. If entropy caps scale with area, there's a finite number of distinct, retrievable configurations inside any bounded patch. Translation: your world line has a bit budget. Not what could exist in principle, but what can be stably distinguished and recovered by you. Past the line, information isn't necessarily destroyed. It's out of reach. Your API call times out. Here's the action step by step. Take a black hole. Semi-classical gravity says a hot horizon radiates. Hawking gave us a temperature. Bekenstein gave us an entropy. Thermodynamics gave us a first law. The area acts like a storage meter. When the hole shrinks, bits leak out as Hawking quanta. Now zoom out to our accelerating universe. Sit still long enough and you find yourself enveloped by a horizon with its own temperature. You won't roast, but the principle holds. There's a maximum number of independent facts your patch can stabilize. The ledger is the horizon. A micro story. A grad stares at a whiteboard. On one side, S proportional to A4. On the other, objectivity equals redundancy. In the center, circled 3 times, cached elsewhere. She isn't being poetic. She's mapping how facts become real. If many copies propagate within your horizon, photons bouncing off a chair into countless directions, the chair's position becomes a stable entry in the ledger. If the copies can't circulate, too far, too thin, beyond the interface, those bits never post. Meanwhile, something else was happening in black hole physics. The page curve, the island formula, quantum extremal surfaces. The math says, when you account for the right region behind the horizon, the fine-grained entropy of radiation bends the right way. Unitarity survives. Information doesn't burn, it re-encodes and streams out. The accountant's note reads, no deletion, recoding with delay, keep that. It matters when we ask what looks like deletion inside our horizon. Complication. Area bounds force hard choices. If you want objectivity, you need redundancy. Redundancy burns budget. Copying isn't free. Landor's principle attaches heat to erasure. In practice, stabilizing facts ties up finite degrees of freedom. You can't have unique high-resolution histories for everything everywhere and keep them all accessible. The interface rate limits you. A world that feels smooth may owe its crispness to merciless compression. Symmetries, coarse-graining, and broadcast of only what many can agree upon. Impact immediate. Horizons reframing the infinite cosmos into bounded instances takes away a comforting illusion. Infinity may exist in the math. Your experience rides a finite channel with area price storage. That's not theology, it's thermodynamics meeting geometry. And it flips a common instinct. We think volume holds the wealth, more space, more room for detail. The ledger says the edge does the counting. Boundaries, not interiors, set the cap. Unknown to them across town, a group simulates light propagation near a cosmological horizon. They watch how signal power thins with redshift and expansion, how modes stretch, how late-arriving photons carry only coarse summaries. The last bits don't arrive. In their plot notes, someone scribbles, "Fidelity drops with distance, prior wins beyond." That's compression under quota. You keep the large-scale shape, lose the micro-flourish. Here, S where everything changes. If facts stabilize by being copied within your patch, then no broadcast means no stabilization. A star just beyond your event horizon isn't part of your objective world, not because it's unreal, but because your ledger can't ever collect the receipts. Inside, facts grow teeth when they ride redundancy. Outside, they remain unsourced variables in equations. This is how a quota feels from the inside. Real where copies circulate, latent where they can't. But there's one problem. If the ledger never truly deletes globally, why do we see gaps locally? Vanishing signals, data that refuses to resolve, budgets blown by early structure. The area law doesn't tell you what the universe will spend bits on. It tells you what it can't exceed. The spending plan, what gets high fidelity and what gets left implicit, emerges from dynamics, causality, and demand. You don't store every voxel. You store what's queried and richly cross-checked. Everything else rides defaults: symmetry, smoothness, conservation. In the aftermath of that night's spike, the grad added one more line beneath cached elsewhere: quota not crash. That's the quiet promise of the ledger. Reality doesn't blue screen when it hits the edge. It compresses, it defers, it encodes on boundaries, it rates limits requests. When you think the map ends, what you're touching is the interface doing its job. To see where overflow lives when the bill comes due, follow the accountant who never loses a line into a black hole's bookkeeping. That's where the universe proves it prefers recoding to deletion. The black hole accountant, where the overflow lives. We left the ledger at the edge. Now we walk through the door everyone swears is a shredder. Start with the stakes. If black holes eat information and radiate only featureless heat, the book doesn't balance. Unitarity, the idea that quantum evolution preserves detail, would fail. That's physics-level bankruptcy. For decades, Hawking's calculation looked damning. Thermal Hawking radiation out, correlations lost, entropy of the radiation climbing until nothing recoverable remained. But something didn't add up. Don Page drew a plot with a different ending, the Page curve. If the whole process is unitary, entropy of the outgoing radiation should rise at first, then, around the halfway mark, peak and fall as correlations leak out. That curve was a dare to the universe. Show me the mechanism. Here, S where the action turns. Semi-classical gravity met quantum extremal surfaces. The island formula told us how to compute fine-grained entropy correctly. You don't naively trace out the interior. You draw a boundary, the quantum extremal surface, whose area, plus the entanglement of fields in a certain union of regions, gives the generalized entropy of the radiation. And then, after the Page time, something wild happens. The optimal region that counts includes an island inside the black hole. The interior gets assigned to the radiation's description. Entropy bends down. The curve behaves. Meanwhile, a small team crowding a hallway printer at midnight watched that plot swing. First runs showed the climb. Then the extremal surface jumped. The island appeared. The line turned over. Someone wrote, "Finally paying back on the margin." That's the accountant's signature. Bits aren't burned. They're recoded, delayed, and in principle retrievable from the radiation. Impact immediate. The ledger keeps unitarity, but there's a catch the size of a wormhole. Retrievable doesn't mean easy. Hayden and Preskill compared an old black hole to a mirror with a lag. Throw in a diary after the Page time, wait the scrambling time, and the message begins to drip back at the Hawking rate. In principle, a perfect decoder with access to all the radiation could read it. In practice, decoding is astronomically hard. Think cosmic scale error correction. The books balance, but the receipts come in a scrambled warehouse you can't inventory before heat death. Complication on top of that, the firewall paradox. If late-time Hawking quanta are entangled with early radiation to save unitarity, how can they also be entangled with interior partners to keep the horizon smooth? Monogamy of entanglement says no double dipping. Something had to give smoothness or purity, or we needed a better map. Holography, complementarity, and quantum error-correcting code stepped in. In code models, the interior is redundantly encoded in the radiation plus near-horizon degrees of freedom, which boundary region reconstructs which bulk operator depends on the global state. No one observer gets both the perfect decode and the gentle fall. For the infaller, the horizon stays dull. For the godlike decoder, the information is outside. No contradiction appears within any single causal frame. Here's a micro story. Two researchers argue over coffee about Python's lunch, the bulge in the entanglement wedge that makes some reconstructions exponentially hard. One says, "It's there, you just can't grab it without Herculean compute." The other shrugs, which is the point. Reality hides by being expensive. They clink mugs, the accountant smirks. Tie this back to our quota. Area counts again. The generalized entropy includes an area term, area over 4G, and a bulk entanglement term. When the island turns on, the area you pay shifts, and the ledger lets correlations reappear outside. Boundaries tally, volumes comply. The edge keeps score so the inside can be written back out slowly. Meanwhile, the global message is brutally consistent with our earlier rule. No global deletion, only local unavailability. Fall behind the horizon and you lose access, not existence. The records move to interfaces you can't query anymore. Later, those interfaces radiate. The world doesn't crash. It rate limits and re-encodes. Now the sting. If overflow never truly vanishes, why do we watch signals die, measurements refuse to sharpen, budgets blow early? Because access is policy. Light cones, scrambling, decoding complexity, and horizons decide who gets what when. The universe honors the audit. It doesn't promise you a front row readout. And there's heat in the margins. Landwehr's bound says erasing a bit costs energy. Black hole evaporation is the ultimate heat for ledger exchange. The shrinking area pays for the outward stream of organized correlations. Every deletion you thought you saw at the cliff is a transfer with a receipt stapled to the radiation bath, illegible without the right key. So what nobody knew at the time the first entropy plots were drawn is what matters now. The accountant lives on surfaces, the overflow lives in entanglement, and lost is a local story told by impatient observers. The lesson is ruthless and hopeful at once. The ledger cares, the universe keeps its books, and what looks like deletion in your wedge is usually a cache miss with a very long retry. Which brings us home. If black holes prove recoding beats erasure, then compression, not annihilation, is the default. The next question is whether the cosmos deletes. It's how it chooses what to keep crisp, what to stream later, and what to leave implicit. For that, you need the doctrine of compression, the rulebook that turns budgets into worlds. Compression doctrine, coarse-graining as reality's default. If the ledger sets the quota, compression writes the story. Not sloppy saving, principled selection. Physics has house style. Keep the variables that survive contact with noise, average the rest, and pay only for distinctions you can actually test. We call that coarse-graining. It's why we talk temperature and pressure for a billion molecules, not every collision's angle and time. Many microhistories, one macro state. Different details, same outcomes within error bars. Efficient on purpose. Here's the stakes line. You don't stabilize every voxel of the world. You stabilize what queries can reach and compare. Objectivity needs redundancy. Redundancy burns budget, and budgets force a shortlist. The rest gets folded into symmetries, conservation laws, and priors that hold until instruments demand more bits. That's not a cop-out. It's how predictions stay cheap and right. Action first. In the lab, Landor pinned a price tag to forgetting. Erase a bit. Dump KTLN2 of heat. You can't clear memory for free, and you can't reset the world without a bill. Now widen the lens. A camera doesn't capture reality. It compresses photons into pixels with a codec built into its sensor and firmware. Physics does something rougher and deeper. Decoherence crushes fragile phases, and the environment broadcasts pointer states. The chair's there because its position correlates with countless photons streaming outward. That's quantum Darwinism. The fittest facts are the ones that copy well. Effective theories are the craft of writing this. You don't model airflow by solving QCD. You use Navier-Stokes on averaged fields valid up to a cutoff. You ignore subgrid turbulence, then add a closure model tuned to experiments. Ugly, maybe, accurate, often better than brute force in the wrong variables. Fluids beat quarks for wings. Phonons beat atoms for heat. Band structure beats Coulomb integrals for semiconductors. Each level picks coarse variables that survive noise and let you predict. Microstory. A sim team faced with a star-forming cloud hits the wall. Full physics runs joke. Too many scales, too few nodes. They draft a subgrid rule. When density crosses a threshold in a bound clump, inject heat and momentum per a calibrated recipe for supernova feedback. Runs finish. Plots match telescope data better than the first principles attempt that crashed. They celebrate, then someone notices parity with an old synthetic map too good. Panic flickers. They rerun with stricter priors, reopen parameters, and the fit loosens, then lands where uncertainty belongs. Lesson banked. Compression can overfit. Keep humility in the loop. Meanwhile, the cosmos practices the doctrine by default. Inflation stretched quantum jitters into seeds, but only certain combinations became the scaffolding of structure. The CMB's acoustic peaks are a compressed checksum. You can fit them with a handful of numbers that summarize billions of microinteractions. Long wavelength modes matter. Short wavelength noise averages out. That's why a smooth early sky carries so much. The initial file was sparse and strong. Complication honest. Compression hides structure until instruments force you to spend. Ask too much of a low bitrate stream and you'll see blockiness. Physics has its version. Gamma ray bursts were used to hunt for energy-dependent delays that would reveal spacetime dispersion. Null. Interferometers looked for holographic jitter. Bounds tight, no shimmer. Smoothness isn't proof of absolute continuity, it's proof the substrate, whatever it is, respects symmetries at a ferocious compression ratio. When upgrades arrive, you might pay for more bits. Until then, priors carry. Impact. This doctrine reframes surprise. When JWST sent back bright early galaxies, the easy story said broken model. The better story said budget shock. Our compression had underpriced early star formation efficiency, dust, emission lines, lensing bias. Spectra shaved some masses, others stayed heavy but not impossible. The fix wasn't mystical. We spent more bits where the data demanded them, adjusted feedback, IMF assumptions, selection functions. The cosmos didn't break rules. Our codec needed a patch. Here's a human moment. A student in a deception lab cuts a 30-second conspiracy short, then makes the debunk. It takes 4 hours to explain what took 15 seconds to mislead. They present both. The class feels the cost asymmetry in their bones. That's the same economics the universe leans on. It's cheap to assert a microdetail. It's expensive to stabilize it. So the world publishes redundancy only for facts that leverage many users. Claims without propagation stay private amplitudes. Tie back to the ledger. Within a finite wedge, stabilization is a resource allocation problem. Lightspeed latency gates synchronization. Horizon area caps distinctness. Decoherence and Darwinism pick bases that travel. Effective theories sit on top, translating coarse modes into laws. The result is a world that feels crisp at the scales we share and soft at the edges we don't. One last micro story. A radio team waits 3 years to catch a nanohertz gravitational whisper in pulsar ticks. When the common spectrum hint strengthens, they don't claim a discovery. They add stations, extend baselines, beat down systematics. Resolution improves because redundancy grows. That's compression in reverse. Spend bandwidth to earn bits. So when something refuses to resolve, signals fade, edges blur, the doctrine offers the sober answer. It's not a crash, it's the codec. You'll get more when you can pay for it. More witnesses, longer baselines, hotter instruments, tighter priors. Until then, reality serves the macro that many can read and caches the micro where it belongs, elsewhere, waiting for demand to justify the cost. JWST's early light, the too soon galaxy problem. Then JWST opened its eye, and the clock we trusted started running fast. Within months, photometry flagged bright, compact candidates at redshifts we used to file under probably noise. Names followed. GNZ11 confirmed anew, then JADES GSZ140, and cousins at Z-1214, galaxies shining just a few 100 million years after the bang, some apparently far brighter than conservative models guessed they could be. Stakes snapped into focus. Either the universe front-loaded complexity, or our compression scheme underpriced the opening moves. Action first, no spin. Early deep fields delivered tight photometric redshifts, teams rushed spectra. A subset slid down the scale after clean lines revealed interlopers, dust, or boosted flux from nebular emission lying in filter gaps. Others held. Where spectra locked, masses shaved, but several remained hefty, still too luminous to wave away. Surface brightness dimming should have buried them. Lensing could have helped, so people built maps and measured shear. Some were magnified, some weren't. A few looked large in angular size, not point-like glitches. Meanwhile, oxygen appeared in one ultra-distant spectrum, metal already in the mix, implying prior rounds of stars. Microstory. A postdoc pours cheap Merlot into paper cups in a windowless room and pushes print. "If this break holds, I owe you a bottle that isn't tragic," she says. The line is clean. The break is where early hydrogen should be. Mass ticks down after a new SED fit, still high. They laugh, then stare at the plot. The toy universe they love just got a more expensive opening chapter. Impact lands across 3 levers. First, star formation efficiency in dense, pristine halos can run hotter than our late-time priors. Cold flows feed early gas. Cooling pathways through molecular hydrogen and metal pore lines quicken collapse, fragmentation shifts. Second, the initial mass function might tilt top-heavy at dawn. More massive, short-lived stars front-load light, seed metals, and bias photometry. Third, feedback timing matters. If the first bursts blow out less than assumed, or if outflows stall in deep potentials, gas turns into stars before winds quench the party. Add selection. We see the luminous tail because that's what we can see. Complication refuses to leave. Surface brightness dimming scales like 1 plus Z4. Clumps, tides, and chaos should dominate morphologies. Yet JWST's resolution shows both. Disorder in many, surprising order in some. An ultramassive red spiral candidate at Z-5 reminds you that disks can settle early under the right streams. At higher Z, most systems stay messy, consistent with youth. Lensing mimics can masquerade as structure. Teams vet arcs, double sources, and chance alignments. Some claims wobble and fall. Others harden under deeper exposures and cross-instrument checks. Meanwhile, simulators sweat politely. Lambdictum isn't dead. It's a scaffolding tied to the cosmic microwave background's acoustic peaks, bow scales, lensing statistics. You don't junk that because a few points defy priors. You upgrade the subgrid rules, radiation hydrodynamics, clumpy media, pop III to pop II transitions, bursty star formation. You widen the parameter priors, sigma 8, small-scale power tilt within bounds, to test whether slightly warmer seeds ease timelines. You fold in nebular line boosting in photometry fits. You propagate lens models, not assume them. The budget balances when you spend honestly. Here's a different micro-story, a lensing map on a tired laptop. A graduate student overlays critical curves on a deep field. One impossible object sits on the caustic, magnified by a factor of several. Another sits in blank sky. They mark colors blue for help, red for standalone, and send it up the chain. The red points are the ones that force physics, not just pipelines. Tease of a specter enters anyway. Papers float alternatives, altered early power, exotic cooling, even dark stars powered by dark matter heating that could glow without fusion and inflate the early light budget. File them under hypothesis, not fact. Most teams stick to the conservative path. Show that more careful accounting, emission lines, dust, lensing, efficiencies, removes much of the tension and leaves the remainder as opportunity, not crisis. The universe didn't cheat. We undermodeled the hustle at dawn. Why this matters for our quota story is simple. Too soon, objects are places where reality chose to spend bits early. You see redundancy in the form of photons crossing baselines, spectra anchoring distances, and independent teams cross-checking catalogs. Those copies stabilize these galaxies as real entries, not hallucinations. Under Quota, you don't get to keep every micro-detail. You broadcast the high-leverage facts. At cosmic dawn, high leverage meant lighting the first beacons that reionize the fog and set structure scales. Compression steered resources to the loud notes. Complication last mile. A few candidates will continue to evaporate under stricter analysis. A few will refuse to budge. That's fine. Rare is not impossible. Blind analyses and null tests, dropping the brightest quartile, scrambling lenses, swapping templates, guard against self-flattery. The plot will move, it always does. The doctrine holds, spend where demand is demonstrable, let priors carry the rest until instruments force you to pay. So no, the sky isn't glitched, it's budgeted. JWST didn't expose a crash, it revealed an aggressive opening bid. Our models respond the adult way, patch the codec, widen the priors, rerun the fits, and accept that dawn wasn't gentle. And with that, we can follow the clock that enforces all this spending. The speed of light render, the latency that decides which facts have time to stabilize and which will always arrive too late to matter. Latency rules, light speed as the render clock. While the JWST debate kept heating in conference halls, the arbiter of what can ever stabilize didn't budge. The speed of light isn't a number, it's a schedule. It sets the render clock for every fact that hopes to become objective. If signals can't make the round trip, nothing gets confirmed, nothing gets copied, and nothing earns a place in your ledger. Start local. Draw your light cone. The backward cone holds everything that could have touched you. The forward cone holds everything you can still affect. Outside those cones is not fake, it's unfetchable. Even in flat space, latency polices reality. Every broadcast takes time. Every cross-check waits on a ping that can't outrun. See, a world assembled from redundant copies has to work with that lag. Scale up and the rule hardens. Expansion stretches the grid itself. Galaxies don't rocket past C. The distance between markers grows. That's how you end up with an event horizon in an accelerating universe. A boundary that future light can never cross toward you, no matter how long you wait. It's not a wall, it's a permanent timeout. Past it, your API returns no route. Meanwhile, something else was happening in timing labs. Pulsar timing arrays chase gravitational waves at nanohertz frequencies, years per wave. Teams log ticks from millisecond pulsars spread across the sky like metronomes. A common spectrum drift hints at a background hum. They don't claim victory. They add stations, extend baselines, wait. That word, wait, is physics, not patience. At cosmic scales, truth arrives on the universe's clock. Here's a micro story. A technician warms their hands on a metal mug at 3 a.m., staring at a residual plot. The fit improves a hair when they fold in a new telescope's data, not enough to tip the scales. They sigh, add another month to the campaign, and tape a note to the rack. Latency is law. It's a joke and a doctrine. You don't rush waves that cross galaxies. The stakes land where sociology and causality meet. Objectivity isn't unanimous opinion, it's overlapping receipts. But receipts require travel time. A supernova goes off in a distant galaxy. Photons sprint at sea, yet expansion drags the finish line. By the time light arrives, the source is older than your records can ever be. Your now is a mosaic of different thens, stitched together by a finite courier. Complication shows up when we try to coordinate across vast regions. There is no global now that all observers can share and render in sync. Each world line builds its own present from signals that actually arrived. That's not philosophy, it's geometry. The upshot is brutal and liberating. Your horizon isn't just a distance, it's a set of deadlines. Miss them, and some facts never make your cut. Impact immediate. Latency explains why redundancy balloons locally while global synchronization never completes. Cities of matter, a cluster, a filament, become crisp where signals can loop, bounce, and cross-check in reasonable time. Out toward the edge of your patch, copies thin, verification lags, and priors start carrying more weight. That isn't a conspiracy to hide detail. It's a bandwidth budget enforced by C. Unknown to them, across town, a radio group models light curves from a lensed quasar. Multiple images flicker with delays set by different path lengths. The delays become a ruler for cosmic expansion. They're literally measuring latency and turning it into distance. The fit improves when they accept that the clock is the map. C writes the geometry, and the geometry writes what can be known when. Here S where the render metaphor earns its keep. In games, far tiles load when you approach. The engine budgets assets by distance and demand. In cosmology, nothing loads, but the only facts that stabilize are those that can travel and be copied within horizons. Light speed is the frame sync. If a request can't be sent and returned, the detail stays implicit, carried by symmetry rather than stored as a record. A human moment brings it down to Earth. A student points a small telescope at a variable star. They log brightness night after night, then mail their data to an aggregator. Weeks later, their points sit alongside hundreds of others on a global plot. The scatter tightens, the period sharpens. What changed? Bandwidth. A single observer had a noisy story. Many observers, spaced by longitude, had a stable fact. C set the cadence. Collaboration filled the gaps. Meanwhile, acceleration keeps moving the goalposts. The cosmological event horizon slowly inches inward in proper coordinates, shrinking the set of events that can ever send you an answer. That's not a doom bell, it's a policy note. As the horizon tightens, the universe will favor local redundancy even more, while distant queries age into silence. Under quota and latency, the pattern is predictable. Truth thickens nearby, thins far away. So when an instrument reports signal fades at the edge, it isn't catching the universe slacking off. It's running into the scheduler. No signal, no stabilization. No loop, no ledger entry. Light speed isn't just fast, it's final. It decides which questions can ever be closed and which will live forever as priors painted across a sky that's still in transit. Voids and cold spots, missing texture or clean compression. While latency set the schedule, the map itself started whispering a different worry. Big empty regions and an old cold bruise on the microwave sky. Stand under a dark patch like the Boötes void, hundreds of millions of light years across, and your first thought is under-rendered. A missing texture pack. But emptiness isn't a bug. It's the outcome of gravity moving mass to the walls and corners, leaving farmland between the highways dark. Here are the stakes. If the universe is running under a quota, emptiness is cheap. Uniform nothing costs fewer bits to describe than complicated clumps. Boundaries hold information, interiors drain it away. So a giant void doesn't violate the ledger, it flatters it. The question is whether the statistics of such hollows fit a cosmos seeded by simple rules, or whether we're looking at a glitch the codec can't hide. Action, no drama. Start with the web. Tiny inflation-born ripples grew into filaments and nodes. Matter flowed downhill, evacuating basins as peaks fattened. Run enough lambdictum simulations with the measured power spectrum, and occasionally you get a Boötes-sized cavity. Rare, not impossible. Surveyors map wedges of sky, count galaxies in shells, and watch dots thin, then nearly vanish. Someone jokes the instrument died. The instrument's fine. The universe just drew a long breath there. Now spin to the older bruise, the CMB cold spot, a few degrees across and cooler than average. The microwave background is a fossil field where temperature variations map density ripples at 380,000 years. Most of it looks Gaussian and well-behaved. The cold spot breaks the mood, big, deep, and alone. You can explain part of it with the integrated Sachs, Wolf effect. Photons crossing evolving structures lose or gain energy. If a giant supervoid lies along our line of sight, it can leave a cooler imprint. Surveys did find an extended underdensity in that direction. Is it enough? Debated. Some analyses say close, others say not quite. Microstory. In a mock sky lab, a grad student injects synthetic voids into a simulated large-scale structure and ray traces CMB photons through them. She tunes profiles, depths, and sizes, then watches the temperature imprint drift by microkelvin. The numbers inch toward the observed dip, then stall. Close, not enough, the advisor emails back. Good, that means we're measuring. They post the bound instead of the boast. It tightens the codec. Complication. Our eyes love patterns. In a survey this large, tails of a distribution will show up somewhere. If you pick the weirdest patch after looking and then ask how weird it is, you'll overestimate surprise. That's why blind tests matter. Teams predefine statistics, freeze their searches, and let the chips fall. Rare isn't damning, it's expected in a big sample. Voids as big as Boötes, low probability, not forbidden. The cold spot. A live split between mild anomaly and mostly noise that refuses to pick a side. Impact lands exactly where the ledger prefers. Empty regions are easy to encode. Smooth fields compress. Complexity hugs the edges. If holographic hints are right and horizons count bits by area, then a void's interior doesn't demand storage. The walls, the gradients where signals change, carry the weight. That's why the web's skeleton eats budget while the hollows feel cheap. Clean compression, not missing texture. Unknown to them across campus, a team cross-checks void catalogs against galaxy bias and survey selection. Are we painting emptiness because we missed faint galaxies? They deepen exposures, adjust completeness, and watch some hollows fill in. Others persist. A second group stacks temperature maps on hundreds of voids to test the average imprint on the CMB. The stack shows a faint dip, consistent with expectations. The single cold spot stays an outlier, loud but not loud enough to topple the choir. Here's where the quota metaphor sharpens the knife. Under budget, you don't spend bits on uniform interiors. You spend on boundaries and exceptions that pull predictions. Voids are default, the codex 0. Clusters are costly, the codex 1. When we point to a hole and say missing, we're saying cheap, and the ledger nods. Smoothness isn't neglect, it's policy. A human moment. A survey lead watches the latest map render on a dim projector. The filamentary web glows, the Boötes void sits like a punched-out pupil. Someone asks if it bothers him. He shakes his head. If the sky were uniformly interesting, we'd suspect a painter. He means it. Noise should dominate where gradients don't. Surprise should live at the edges. Tease softly. If the cold spot survives every blind test and alternative foreground model, then we'll need either a subtle feature in the initial power, a relic from pre-inflation physics, or a line-of-sight stack we undercounted. Until then, discipline beats romance. The sky doesn't owe us narrative symmetry, and the codec isn't hiding brushstrokes, it's obeying constraints. So no, the empty rooms aren't under-rendered. They're rendered as absence, cleanly and cheaply. The bruise on the old light is a question mark, not a confession. In both cases, compression wins where redundancy would be wasted. And if you're hunting for the substrate's shimmer, you won't find it in hollows. You'll need to listen for pixels in the dark, discreteness that hides by canceling its own chatter. Pixels in the dark, discreteness without jitter. If the codec is ruthless and the ledger lives on edges, the next question is obvious. Is the substrate itself pixelated? People point to the Planck length, about 1.6 times 1035 meters, and the Planck time, about 5.4 times 1044 seconds, and say there's your grid. Careful. Those scales are where our current theories stop being trustworthy, not squares etched into space. They mark the failure of classical smoothness and plain quantum rules when gravity joins the party, not a checkerboard you can photograph. Here are the stakes. If space is granular, why don't we see the shimmer, the dispersion, the fuzz, the random walk in phase? If discreteness is real, it hides exceptionally well. Experiments went hunting where the signal should amplify with distance. Gamma-ray bursts throw photons across billions of light years. If high-energy photons crawled through space a hair slower than low-energy ones, long flights should stretch arrival times into detectable offsets. Teams crunched the light curves. Bounds got tight. No systematic delay within sensitivity. If there's grain, it cancels its own chatter. Action next. Interferometers tried to catch holographic noise, correlated jitter you can't blame on mirrors, air, or lasers. Clever cross-correlation set upper limits again and again. Smoothness holds to brutal precision. Meanwhile, high-resolution timing from pulsars and magnetar flares offered natural laboratories. If spacetime were a sloppy lattice, phase would decohere over long baselines. It didn't within error bars. The silence is loud. Any granularity respects Lorentz symmetry to a degree our instruments can't insult. Microstory. A small collaboration builds a tabletop instrument designed to hear correlated flicker at Planck-adjacent scales. Months of data, careful subtraction, dead ends. The final plot is flat within bounds. They publish a limit, not a buzz. At the debrief, someone shrugs, half proud, half deflated. If there are pixels, the anti-aliasing is absurd. The room laughs. The point lands. Compression can hide the substrate by design. Black holes keep pressing the case for boundaries. Bekenstein, Hawking entropy scales with area, not volume. The number of internal configurations you can hide goes like the horizon's area in Planck units. A 4G Hawking radiation gives horizons a temperature. Gibbons. Hawking extends it to cosmological horizons. Entropy means microstates. Where do they live? Every road bends towards surfaces and entanglement across them. Holography turns that into a principle in solvable setups. Bulk geometry maps to boundary quantum degrees of freedom. Our cosmos is anti-de Sitter, but the area law keeps showing up like a refrain. Complication. Discrete doesn't have to mean grid. Quantum gravity candidates don't agree on pixels you can draw. Loop gravity talks about quantized areas and volumes, spectra, not tiles. Causal sets build spacetime from partial orders, events linked by causality rather than coordinates. Spin foams, tensor networks, error-correcting codes in holography. Every language points to structures whose coarse-grained behavior is the smooth metric we measure. The discreteness, if real, may be relational and hidden. What propagates are long wavelength modes that average over the mess so well you can't tease out a shimmer. Impact immediate. Smoothness isn't an argument against granularity, it's evidence of ferocious symmetry. Whatever stitches spacetime together cancels low-order violations of Lorentz invariance to absurd precision. That's compression at work. Only the modes consistent with symmetry and conservation make it out of the substrate. Everything else destructively interferes. The absence of flicker is a positive result. It tells you where not to spend your speculation budget. Meanwhile, black hole bookkeeping narrows the room for naive pixels. The island formula, generalized entropy as area over 4G plus bulk entanglement, says boundaries carve the problem into pieces and the fine-grained ledger behaves. That isn't a picture of bits flipping on a lattice. It's a calculus of regions, surfaces, and codes. Python's lunch makes decoding hard without breaking unitarity. Reconstructing the interior from the outside becomes exponentially costly, not forbidden. Geometry measures complexity. Microstory. Two theorists stand at a whiteboard. One sketches a tensor network and says, if there are atoms of space, they aren't arranged on a square. Think language, not pixels. The other draws a curve labeled cost and a bulge in the middle. Python's lunch, she says. Accessible in principle, hopeless in practice. They grin. They've just turned a metaphysical panic into a performance note. Complication you can't dodge. We still don't have a complete quantum gravity for de Sitter space, the one we live in. Holographic duals are clearest in anti-de Sitter boxes. Translating area laws and error-correcting intuitions into our accelerating universe is an active fight. De Sitter entropy exists, so does a horizon temperature. Entanglement wedges, quantum extremal surfaces, complementarity, they have analogs but proofs thin out. The ledger's handwriting is legible. The full audit trail is still in draft. Tie back to our quota. If bits scale with area, any finite horizon sets a finite maximum on distinct, recoverable detail in your wedge. Try to cram more and the physics pushes back. Collapse, thermalization, decoherence. Under that cap, The world we see is the efficient projection of something richer, with redundancy poured into facts that travel and symmetries policing what remains implicit. So are there pixels? If there are, you won't catch them in arrival lags or handheld interferometers. You'll meet them in area laws that outvote volumes, in entanglement patterns that reconstruct insides from edges, in symmetries that smother jitter, and in codes that make bulk operators state-dependent. Discreteness without shimmer, grain without grit. And that points the way to the place that wrote the first compressed file. The sky's smoothness, the CMB's peaks, the near-scale invariance that seeded everything. Something did ruthless compression early. To understand how the ledger got its opening entries, we have to rewind
Inflation's
to the pen that wrote them. Minimal inputs, maximal universe. To see why the sky looks organized with so little time, we have to go back to when space was barely a word. Inflation is the move that sets the board, a fraction of a second of runaway expansion that takes a tiny, causally connected patch and blows it up to cosmic size. Not matter racing through space, but space itself stretching so fast that regions once neighbors become strangers forever. Here are the stakes. Without inflation, 3 headaches don't fade. First, the horizon problem. Opposite sides of the microwave sky share the same temperature to absurd precision, yet in a slow-expanding universe they never had time to talk. Inflation says they did before the stretch. Second, flatness. Spatial curvature dilutes like wrinkles on a sheet pulled tight. Inflation irons them. Third, seeds. Quantum jitters in fields get promoted to macroscopic ripples, the scaffolding of galaxies. 1 brief act, 3 debts paid. Action stripped of romance. Picture a field with potential energy, call it the inflaton. While it lingers on a flat section of its potential, energy density stays nearly constant. Space inflates exponentially. Everything cools by dilution, not by radiating away heat. Modes of quantum fluctuation start small, oscillate, cross the horizon as inflation outruns them and freeze. When inflation ends, reheating energy in the field decays into particles and radiation. Later, as the universe slows, those frozen curvature perturbations re-enter the horizon and gravity turns them into structure. That trail is visible in the acoustic peaks of the cosmic microwave background, a drum chart of the early plasma. Microstory. A theorist at a whiteboard writes NS approximately 0.965 and taps the number. That slight tilt in the primordial spectrum, more power on long wavelengths than short, is what precise CMB experiments measured. It matches simple inflationary hills. It's not exactly 1, she says, and that imperfection is the signature. A student photographs the scrawl before the board gets wiped. The slope on that curve is $1 million constraint. Impact lands as compression. Inflation writes a sparse instruction set, amplitude, tilt, a handful of parameters, and the universe elaborates. You don't need to specify every voxel of initial conditions. You specify a few statistics, then let gravity, radiation, and chemistry do the rest. The CMB becomes a checksum you can fit with half a dozen numbers. Given our quota story, that economy isn't cosmetic, it's policy. The opening file is small and strong on purpose. Complication shows up at the edges. We've chased B-mode polarization, curl patterns imprinted by primordial gravitational waves for clues to the energy scale. So far, upper limits, not a detection. That rules out some large field models and leaves others alive. Subtle anomalies hang around. Low quadrupole power, alignments of low multipoles, hemispherical asymmetry. They might be statistical flukes. They might whisper features in the potential. Discipline says, note them, don't overfit. Meanwhile, alternatives press for a hearing. Some teams argue you can blend quantum fluctuations with modified gravity to mimic inflation successes without an extra field. Others propose features in the inflaton potential, brief pauses, kinks that could explain small departures without wrecking the peaks. Eternal inflation, the idea that some regions keep inflating while others stop, buds a multiverse of pockets with different properties. Evidence, not directly. Interesting, yes. Established, no. Unknown to them across town, an observational group fits Planck, bow, and supernova data with inflationary parameters. The posterior peaks where the simple models live. When they allow a small running of the spectral index, the fit barely improves. Someone circles the plot's narrow valley. "Sparse wins," she murmurs. It's not a slogan, it's the data's taste. Tie back to compression and the ledger. Inflation's genius isn't speed for its own sake. It takes a small, equilibrated patch, one ledger already balanced locally, and scales it up so that our entire observable universe inherits that equilibrium. The cosmic horizon we live under carries a finite entropy proportional to its area. Inflation bootstraps that interface by making sure the stuff inside obeys simple, broadcastable rules. The uniformity isn't painted. It's a memory of intimacy stretched thin. Microstory. In a seminar, someone asks if inflation explains everything. The speaker shakes his head. "It explains why we can explain," he says. "It gives us the right initial data, nearly flat, nearly Gaussian, nearly scale invariant." The room relaxes a little. Humility is part of the model. Complication, honest and current. We don't have a complete holographic dual for de Sitter space, the accelerated background relevant during and after inflation. The island formula and quantum extremal surface tools, which advance the black hole information problem, are sharpest in anti-de Sitter boxes. Translating those tools to our world is active work. Still, the area laws, the temperature of horizons, the success of inflation's predictions, they lean the same way. Boundaries count. Simple initial statistics travel far. Impact final. When JWST surprised us with bright early galaxies, the fix wasn't to throw out inflation's pen. It was to revise how quickly the later chapters write themselves. Star formation, feedback, dust. The opening paragraph stands. The acoustic peaks haven't budged. The tilt still whispers a gently rolling field. B modes remain a bounty on the table, not a debt. Sparse inputs, maximal reach. So the ledger's first entry isn't a brute list of details. It's a compact rulebook that tells a finite horizon world how to spend bits wisely. Write uniformity broadly, seed variety lightly, and let dynamics allocate redundancy where demand will be greatest. If deletion is a fear, inflation shows the counter-strategy. Compress early, broadcast the essentials, and give evolution room to improvise. Dark energy's quiet quota, the cost of empty space. We've been counting bits on edges and watching inflation write a small, strong opening file. But there's a background process that never logged off, a charge on emptiness itself. Call it dark energy. It doesn't clump, it doesn't shine, and yet it owns most of the ledger. Not because it stores detail, but because it taxes the space that tries to. Observations point to an equation of state near W approximately -1, consistent with a cosmological constant, with alternatives like slowly evolving fields remaining actively tested. Here are the stakes. Observations from supernovae, baryon acoustic oscillations, and the cosmic microwave background agree. The universe's expansion is accelerating. In a cosmos where gravity pulls, acceleration means something else pushes. The simplest model is a cosmological constant, vacuum energy that stays the same per unit volume as space grows. More space, more total nothing, more push. The bill is cosmic. Geometry bends, horizons form, and every observer inherits a finite patch with a finite entropy proportional to horizon area. The quota isn't a metaphor. It's the ambient policy of de Sitter space. Action clear. Teams in the late 199 saw distant Type Ia supernovae dimmer than expected, farther away than a decelerating universe would place them. Fold that in with CMB peak positions and bow rulers, and the fit lands near a flat universe with about 70% dark energy, 25% dark matter, and a thin slice of ordinary matter doing the visible work. That mix draws a future with an event horizon. Even if you wait forever, some regions can never message you. The Gibbons-Hawking temperature of that horizon is cold. Its entropy scales with area. The ledger whispers, your accessible distinctness is bounded by an edge that's moving, quietly rewriting what reachable means. Complication bites hard. If vacuum carries energy, why is its density so small? Quantum field theory naively sums zero-point energies of modes and overshoots observations by a vast margin. That's the cosmological constant problem, one of the worst budget mismatches in physics. You can try to cancel terms with a bare constant. You can speculate about symmetry that sets it to zero and dynamics that lift it to a small positive value. You can swap the constant for a field, quintessence, that evolves slowly. But every move pays a price. Fine-tuning, new particles, new couplings, new coincidences. Microstory. A cosmologist pins a sticky note above her monitor. Lambda small, non-zero. It's a joke and a constraint. When she runs fits with new weak-lensing maps and bow catalogs, the data keeps coming back near a constant-in-time vacuum energy. No strong evidence for dynamics yet. She stares at the posterior like it's hiding a trick. It is. Simplicity wins uncomfortably. Meanwhile, survey teams build geometry as an audit. Weak lensing shears galaxy shapes, clustering sketches standard rulers. Supernovae tick through light curves. They don't measure lambda directly. They measure how space expands and structures grow under its pressure. If dark energy is a constant, growth slows in a specific way. If it's a field, small deviations appear in the growth index, and the equation of state parameter W so far, W hovers near -1. The ledger prefers boring and inexorable. Impact immediate. A positive vacuum energy gives every observer a de Sitter, like horizon with finite entropy. That sets a hard cap on distinct, recoverable information in your patch, regardless of how clever your instruments become. As acceleration continues, the event horizon's proper distance settles. The number of bits your wedge can distinguish saturates. Under our quota story, that's the quiet quota. Empty space bills you for area and locks in a maximum balance. Complication social. In a world where most of the budget is nothing, apparent deletion takes on a new face. Signals from distant structures redshift and fade. Past a threshold, they dilute beneath any finite detector's noise. Galaxies that once contributed to your ledger drift beyond your future light cone. For you, their facts stop stabilizing. In the archive, this can look like drift to nowhere, data thinning without drama. It isn't malice, it's policy enforced by accelerated expansion. Unknown to them, across town, a theory group tries modified gravity instead, tweaking the left-hand side of Einstein's equation to mimic acceleration without vacuum energy. They fit background expansion and growth simultaneously. Some FR-like models slip past first gates, then stumble on lensing or cluster counts. The healthiest versions bow to screening mechanisms to keep solar system tests intact. The message is pragmatic. Whatever you call it, lambda or a cousin, the geometry demands a shove that looks like repulsion on large scales. Microstory. A graduate student plots the Hubble diagram with and without peculiar velocity corrections. The scatter tightens, W's error bars shrink a hair, and the best fit nudges back toward -1. He grins, then deletes a tweet draft. Let the systematics breathe, his advisor says. They both nod. In this business, premature precision is a kind of fiction. Tie it back to the ledger. Dark energy doesn't spend bits. It sets the ceiling and manages access. It creates the event horizon that rates limits what can ever be fetched. It stretches wavelengths, lowering photon energies, and turns once-detailed messages into coarse hints. The cost of empty space is not detail, it's permanence. Questions that could, in principle, close inside a decelerating cosmos age into priors under acceleration. The archive thins at the edge, the budget freezes. So when we talk about deletion in this story, the darkest version isn't a shredder, it's a soft lock. Facts beyond the horizon never enter your redundancy network. Facts near the edge degrade into summaries, distances, dipoles, bulk flows. The universe doesn't erase, it amortizes. And as lambda rules the long game, the amortization schedule hardens. The quota goes quiet and absolute. And that brings the story home. If the background bills us for area and enforces timeouts, then the only deletion we can control is local, what we choose to copy, preserve, and broadcast before the edge turns questions into silence. Evidence versus spectacle, when the fake outshines the real. We've spent an hour with horizons, budgets, and the physics of what can and can't be fetched. Now the cruel mirror. Even inside our wedge, even when photons arrive and receipts exist, spectacle can bury evidence. Under quota, redundancy stabilizes truth. Under feeds, repetition stabilizes feeling. Those look similar until you ask who's doing the copying and why. Here are the stakes. If reality spends bits on what many can verify, a platform spends bandwidth on what many will replay. Smooth, hyperreal fabrications fit the codec of attention better than scarred, authentic records. Grain, scratches, unstable contrast, the marks that make a thing real, read as errors when the feed expects high-gloss certainty. The smoother lie gets more copies. Copies look like consensus. Consensus feels like truth. Action practical. A side-by-side rolls on a classroom monitor. On the left, an Apollo visor reflection lends flare, film grain, dust that clings and falls wrong by Earth standards. On the right, a generative clip with studio lights, crisp shadows, zero noise. The room's first pass is predictable. Students favor the fake. It matches their priors about what clarity should look like. Then we toggle contexts. Lunar reconnaissance orbiter images of descent stages. Laser ranging returns off retroreflectors still on the moon. Independent captures from India's Chandrayaan and China's Chang. The provenance thickens. The lie doesn't. Micro-story. A teacher runs a prebunking drill. She opens with a short gotcha about a flag rippling. The class nods. Then she shows the source sequence uncut, explains inertial damping in a vacuum, and plays a lab demo with a dangling cloth in low pressure. The trick evaporates. 2 weeks later, the same students spot a recycled variant in their feeds and post the correction themselves. That's redundancy with a purpose. Meanwhile, algorithms optimize for spike. A clip that suggests fakery outruns a slow explainer because anger and surprise drive watch time. One click triggers 10 more along the same theme. The path feels like discovery, it's just a gradient descent on engagement. Psychology amplifies it. Community forms around defiance. Phrases like wake up and open your eyes perform belonging. Inside that ring, authentic scars look like fraud markers because polish becomes the badge. Complication honest. Archives alone rarely flip minds primed by mistrust. A terabyte of scans doesn't compete with 30 seconds of music and certainty. You need inoculation, not just rebuttal. That means showing how a deception is built before it hits, then letting viewers take the wheel. Hands-on microcons constructed and debunked in the same session. The memory sticks because they made the error themselves and felt the fix. That's how you turn spectacle toward receipts. Parallel action. A creator on TikTok opens with a familiar hook, "What NASA didn't show you," then cuts the reveal mid-beat. "Here's the edit I just did." Frame by frame, they lay out how selective cropping and mislabeling turn a maintenance shadow into a studio rig. Comments swing from caught to "oh." That flip is small but real. It works because the platform's cadence wasn't rejected, it was co-opted. Impact structural. In a finite horizon world, objectivity is broadcast redundancy. In a feed world, virality is broadcast redundancy. The difference is provenance. Physics forces rate limits and receipts, light cones, timestamps, independent baselines. Feeds don't. So the tactic is to drag platform redundancy toward physics redundancy. Stitch chains of custody into formats that travel. Stack independent confirmations into shorts that feel native, and reward habits that pause rather than swipe. Micro-story. A museum digitizes a mission reel with telemetry overlays and synchronized ground-to-space loops. Instead of a polished trailer, they release micro-slices. A thrust trace over a descent frame, a clock match to a seismic ping, a crossfade to a present-day laser shot hitting an Apollo reflector. Each segment stands alone in the scroll, but also links to the others. 1,000 strangers assemble the chain out of order and land on the same ledger entry. Complication economic. Engagement engines penalize friction. Accuracy requires it. There's no cheat for that. The workaround is craft. Hooks that promise a reveal rooted in proof. Cliffhangers that lead to context instead of outrage. Humor that lowers defenses long enough for a receipt to land. Transparency helps more than swagger. We don't know yet reads as trust when followed by an update. Unknown to them across town, a public archive flags a synced metadata error in their own upload. They post the correction instantly, pin it, and leave the mistake visible with a note. The crowd moves on without a pylon. Quietly, the archivists earn something algorithms can't mint, a reputation for not papering over rough edges. That reputation is a redundancy multiplier. People copy what they trust. Here's the line that ties it back to horizons and quotas. In physics, a fact stabilizes when copies propagate within your light cone and survive attempts to scramble them. In feeds, an artifact stabilizes when copies propagate within your social graph and survive boredom. The cure isn't to sneer at spectacle. It's to teach the interface, ours and theirs. Read the platform, slow your reflexes, demand independent lines, and design for propagation that carries receipts, not vibes. One last human moment. A student who fell for 3 hoax edits in September sits in December editing a short about JWST's oxygen detection at high redshift. They cut in the spectroscopic line, the instrument ID, the proposal number, and the independent team's verification. Comments argue about cosmology instead of authenticity. Progress. Under Quota, that's a win. One more fact copied well enough to outlive the interface. Inoculating against deletion by feed. We've shown how physics stabilizes facts through redundancy. Now we turn the lens on us. The interface using feeds designed to delete context faster than we can copy truth. The stakes are blunt. If attention engines reward smooth lies and punish scarred receipts, you won't just lose a debate, you'll lose the ledger. So we train resilience, not reverence. We teach the interface. Start with reading the platform. Students watch a viral hoax clip straight from their own feeds, jump cuts, ominous bass captions that answer before the question forms. The instructor freezes frames and asks only about craft. Why that crop? Why that font? Why that beat drop on the claim? Hands rise as the penny drops. The video's argument is the editing. Once they recognize the pattern, the next clip feels less like a revelation and more like a pitch. That shift matters. It creates the pause where evidence can land. Then prebunking. Don't wait for the rumor, stage it. A lab segment begins with a fake, a waving flag or a shadow at a strange angle. The students replicate it themselves. Hang a cloth in a vacuum bell jar and watch it wiggle after a twist, or move a single light across a rough terrain to make impossible shadows. They build the trick, then break it in the same session with uncut footage and primary sources, mission timelines, instrument readouts, independent confirmations from multiple space agencies. The memory sticks because it's embodied. They didn't just hear a correction, they performed the error and felt it collapse. Next, the build and bust microcon. Each team designs a 30-second hoax in the platform's native style, posts it to a closed class channel, then produces the debunk that maps every edit to an intent. They track which format spreads faster and why. The discussion turns tactical. Hooks are not the enemy. Unreferenced certainty is. A student who thought context kills engagement learns that a spectrograph line with a clean label can be its own cliffhanger if you script the reveal right. Bring in hands-on chains of custody. A museum partner supplies digitized reels with telemetry overlays and synced ground audio. Students cut them into micro slices that travel, thrust trace over descent footage, a laser-ranging timestamp paired with a modern return, a crossfade to an independent orbiter image. Each short links forward and back, so random viewers assemble a complete provenance out of order. The result isn't a lecture, it's a distributed ledger, native to the feed. Layer nudges. Before any share, the interface throws a speed bump. Who else has this? It's not a moral plea, it's a cognitive interrupt. Students add 2 independent sources, preferably from different institutions or nations, before posting. At first, they groan. 2 weeks in, the habit becomes a reflex. When an eye-catching claim appears, they search for the second path. If none exists, the clip drops to interesting, unverified, not an identity, just a state. Micro-story. In one class, a quiet student runs a live stream where she promises what NASA didn't show. Thousands join. Then she flips the frame. Here's what I cut out to make you click. She scrubs through her own edits, labels every omission, and stitches the missing shots back in telemetry, instrument IDs, a second nation's angle on the same event. Comments turn from gotcha to process. She didn't lower the platform's energy. She redirected it to receipts. Teach error culture. Institutions earn trust by surfacing mistakes quickly, pinning corrections, and leaving the original visible with context. Students simulate an archive drop that mislabels a timestamp. They issue a correction within minutes, tag the fix on every downstream clip, and track how fast the patch propagates. The lesson lands. Transparency is a redundancy multiplier. Hidden edits breed conspiracy. Visible fixes breed tolerance. Run blind analyses. Split the room. Half the students get the data with the headline. Half get only raw files and a task to define tests in advance. When results converge, confidence rises for the right reason. The method survived contact with bias. When they don't, the debrief asks where the framing pulled. They feel, not just hear, the danger of post hoc stories. Calibrate incentives. Grades reward documented provenance, not just views. A slick short earns nothing without a chain that others can replicate. Conversely, a lo-fi clip that gets 2 independent confirmations and a civil thread exchange outruns polish. You're not punishing style, you're paying for redundancy. Fold in creators. Invite a TikTok educator who debunks in native cadence. They show how to hook without lying. Question, reveal, receipt, tease, context, handoff link. Students watch a live cut. A JWST spectrum with the line masked, a beat of suspense, then the label slides on instrument, exposure, proposal ID, and a jump to the independent team that confirmed. Retention spikes without bending the ledger. Micro-story. A school runs a deception lab across science and civics. By the end of term, the same cohort that boosted a polished fake in week 1 now auto-tags a chain for a new claim. An orbiter image, a terrain match, a foreign agency's confirmation, a time-stamped log. The clip travels with its receipts attached. The comments argue substance, not existence. That's a cultural flip you can measure. Finally, institutionalize the pause. Read the platform, find 2 paths, show your receipts into onboarding for students, staff, and community partners. Publish your correction protocol. Push your raw data with tools that let outsiders stitch their own chains. You won't stop every hoax. You will raise the cost of deletion by feed. This isn't media literacy as a scold. It's engineering redundancy for minds. In a finite horizon world, truth survives by being copied across independent channels. In a feed-saturated world, that's a skill you can teach. Train the interface, and your wedge keeps more of what matters. The interface view, rendered, cached, and out of reach. Think of horizons as APIs, not walls, interfaces. What you can ask, what comes back, and how much detail can ever stabilize all depend on the surface you're calling and the user you are when you call it. Mix up the interface, and you'll swear files are missing when they're just stored somewhere you can't reach. Start with the menu. There's the particle horizon, the farthest light that has arrived so far. There's the event horizon, the boundary beyond which future light can't ever reach you in an accelerating universe. And there's the apparent horizon, a local right-now surface where outgoing light skates the line between escaping and getting dragged back. They sound similar, but they answer different queries. Shift your motion, change your world line, and your apparent horizon moves. 2 users, 2 dashboards, same backend. Thermodynamics sneaks in. A de Sitter, like Cosmos, assigns a temperature to its horizon, the Gibbons-Hawking whisper, and an entropy proportional to horizon area. That's the boundary ledger again, a finite count of distinguishable states accessible to your instance. If bits scale with area, your wedge has a storage quota. You don't blow past it by clever coding. The interface rate limits you. Microstory. A team runs a visualization of light rays near a cosmological horizon. Signals from a fading source dribble in slower, redder, then smear into the bath. Someone writes cached elsewhere on the whiteboard and circles it. They aren't being cute. The simulation shows data sliding behind an interface you can't cross. The source's details still exist in the global state, just not in your inbox. Here's the practice, not the poetry. Inside your patch, facts can stabilize because signals circulate and copy. Photons scatter, records multiply, cross-checks complete. That's rendered. Beyond your event horizon, no future request can return. That's out of reach. Between them sits a third category, cached. These are correlations you could, in principle, recover if you had the rest of the system. The right radiation, the right decoding, the right wedge. Black hole islands taught us the trick. After the page time, parts of the interior belong to the radiation's description. But you don't get both the soft fall and the perfect decode. The interface enforces perspective. Complications become policy. Rate limits show up as lightspeed delays and scrambling times. Storage quotas show up as area laws. Redundancy inflation shows up as quantum Darwinism. Pointer states broadcast through the environment. Observation isn't will. It's joining the network that copies the outcome. The world renders where copying goes wide. It remains implicit where copying can't complete. Microstory. An astronaut in a far future drifts in dark energy's deep time. Their apparent horizon sits closer than ours did. The sky is emptier. Their detectors still see a thermal bath at a horizon temperature too cold to warm a hand. They log it anyway because that cold noise is a bookmark. Here, your interface. Here's your quota. The data's boring. The meaning is. Observer dependence doesn't mean anything goes. It means objectivity is scoped by access. And in Fowler's interface returns smooth horizon. A distant, absurdly patient decoder's interface returns interior recoverable from radiation. No one can query both simultaneously. Entanglement structure is the permissions table. Light cones are the firewall. Now translate the metaphor into 3 return codes. Rendered, high redundancy inside your wedge, facts stabilized, receipts everywhere. Cached, information encoded non-locally, accessible only with a coalition of degrees of freedom you don't hold. Out of reach, events outside your event horizon, no route ever. Most confusion comes from sending the wrong request to the wrong surface and blaming the server. Holographic hints keep the mapper honest. Boundaries tally, volumes comply. The generalized entropy you compute is area over 4G plus bulk entanglement. When an island turns on, the boundary you pay for shifts, and information you thought was inside moves into your wedge's description. That isn't a miracle. It's the interface redrawing which files belong to your account. Microstory. A student stares at a delayed choice eraser plot and whispers, "It's like the past waits for the question." The advisor shakes his head. It waits for the context. Context is just which interface did you call with which degrees of freedom. Change the coalition, change the cache you can mount. Tie it to practice you can feel. Telescopes are interface clients. Within your particle horizon, more time and bigger mirrors return more redundancy, facts sharpen. Within your event horizon, some queries asymptote, redshift saps energy, signals fall below any finite threshold. The user experience is a fading map edge, not a lost file. The platform didn't delete your galaxy. The API timed out. Rate limits matter at home too. You can't stabilize a claim about a mission, a measurement, a miracle, without copies that survive independent fetches. If you push a story that never leaves a private channel, it never renders as public fact. That's not censorship, it's physics scaled to society. Our interface, institutions, archives, open protocols, decides what gets cached across minds. So when you hit an edge and feel deletion, check the interface. Ask, is this rendered here? Is it cached elsewhere? Or is it out of reach for me from here on this horizon's clock? The answers won't flatter impatience. They will keep the ledger straight. Life in a compressed world. What you stabilize matters. If horizons are interfaces and quotas are real, meaning doesn't vanish. It narrows to what you can actually make stick. In a compressed world, agency is the physics of keeping. A choice only becomes real when it propagates, when the environment carries it in copies that other observers can fetch without you. Start where it hurts and helps. Redundancy is expensive, so point it. A promise whispered once is amplitude. A promise documented, time-stamped, cross-checked, and picked up by others is a fact. The same rule that makes a galaxy real, photons duplicated across baselines, spectra-locking redshifts, makes a civic norm real when it's recorded in transparent logs, repeated in behavior, and auditable by strangers. Skepticism isn't the enemy. Unfocused doubt is. Direct it toward verification. Who else saw it? Where is the independent channel? Can we rerun the fetch? Microstory. An astronomer designs a radio array she'll never see complete. The baselines require decades. She writes proposals, hires apprentices, argues through budget winters. 10 years after she's gone, a whisper in Pulsar ticks Titans into evidence. Her name sits mid-author list, but the real monument is redundancy. Stations on 3 continents, clocks disciplined by distant quasars, a hum that survives format shifts and retirements. She didn't control results. She stabilized the machine that would. Reachable versus unreachable clarifies leverage. You cannot push a star 10 billion light-years away. You can build sensors that last, archives that outlive formats, institutions that correct in public. Design choices echo. Open protocols multiply copies. Brittle silos die quietly. A dataset that only one tool can read is unrendered for most users. A dataset with checksums, mirrors, and human-readable context renders almost anywhere. Same bits, different survival odds. Latency reframes patience as practice. Some projects take longer than your own coherence time. Accept it. Write documentation like a message to someone who has never met you. Publish raw and processed forms. Pair claims with the pipeline that produced them. Leave enough trail that a cold start can catch up after your horizon closes. That isn't romance. It's how you beat timeouts. Microstory. A coastal town installs a tide gauge network on a shoestring. Volunteers swap batteries, post weekly photos of the same pier, upload CSVs to a public drive. 5 years later, a storm surge threatens. The record turns from hobby to baseline. Engineers model the floodplain using that messy archive. Insurance policies shift. Building codes update. None of it glitters, but every step is a copy, a ledger entry that survives scrutiny. Humility is part of the physics. Quotas apply to you too. You cannot carry every cause. Pick leverage over spectacle. Ask what instrument you can build, literal or social, that others will keep running. Ask which habits install easily. A pre-share pause, a two-source check, a correction protocol you're willing to use. The goal isn't invulnerability, it's resilience through propagation. Collaboration is a thermodynamic hack. Objectivity scales when many observers carry the same record independently. That's true in telescopes and in towns. Push your work into federated spaces, multiple hosts, mirrored repositories, foreign partners. Shared stewardship is a redundancy multiplier. It earns trust the way physics does, by surviving translation and distance. Microstory. A student group launches a microsatellite with a cheap camera and an absurdly careful chain of custody. They publish pointing data, calibration frames, orientation logs, and a public API. Amateur astronomers write clients in 3 languages and start cross-checking images with ground observations. A glitch appears. The students post it, patch it, pin it. The audience grows precisely because the scars show. Here's the sobering edge. As acceleration thins the far map, more of your meaningful work will be local. Habitats, archives, instruments, skills that copy well across short hops. That isn't fatalism, it's focus. A world bounded by horizons is generous nearby. Invest there. Teach the interface. Build the ledger you want to inherit. Last microstory. A teacher tapes 3 sentences to a classroom door. Read the platform. Find 2 paths. Show your receipts. At year's end, her students don't cite her. They repeat the lines to others. The words aren't wise, they're portable. They ride the environment. In a compressed world, that's impact, choices that become real because they copy. So pick what you'll stabilize. A habit, a dataset, a norm, an instrument. Make it easy to fetch, hard to corrupt, and tempting to reuse. Let skepticism live, but root it toward checks. Under quota and latency, that's agency, broadcasting the few facts you can keep long enough for someone else to catch them. Deletion isn't loss. It's a quota that forces us to build truths that travel and let the rest stay implicit. If this frame shifted how you see horizons, evidence, and agency, subscribe for the next chapter on dark energy's tightening horizon. Watch our deep dive on black hole bookkeeping, and drop the one deleted fact you'd restore, plus how you'd make a copy everywhere.